Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. And very good evening to all delegates, distinguished guests, and conference organizer. Before we and welcome to keynote speech number 6. Yeah, so this is number 6. Before I introduce the speaker to the audience, I'd like to maybe introduce myself first. I'm Ishak Aris from University Putra Malaysia. It is in Sedang. If you go to Kuala Lumpur, it is about 30 minutes from city center of Kuala Lumpur. Yeah, it's very close to Kuala Lumpur city center. Okay, my background a little bit. I work a lot on currently now on EV and also autonomous vehicle as well. Yeah, that's my research area. Okay, now I'd like to introduce the speaker for today. Yeah, so we have Dr. Ashitey Trebi-Ollennu. Yeah, so the topic for today is the role of telepresence in future mission, future space mission. Okay, so let me read a little bit background of Dr. Ashitey. So he's a principal robotic engineers, deputy chief engineers, and assistant division manager of the autonomous system, division 34 at NASA Jet Propulsion Laboratory, California Institute of Technology, United States of America. He also served as the chief engineer for mobility and robotic system section from 2017 until 2020. Product delivery manager for Inside Mars mission instrument deployment system, and also Inside Mars mission instrument deployment system operation team chief. Yeah, he also member of IEEE steering committee on Telepresence. So without further ado, I'd like to call upon Doctor to deliver the speech. Thank you.
Hey, thank you, Professor Aris. Welcome. So today I'm going to talk to you on behalf of the IEEE Telepresence. We've been looking at the future of telepresence, and we have a big conference coming up in November at Caltech in Pasadena. I've been looking at the role of telepresence in space missions and what we've been doing in NASA as a whole. So that's what I'm going to talk to you about today. So in 1980, quite a long where a foresighted Professor Minsky said, telepresence is not science fiction. And he said we could have a remote control economy by the 21st century if we start planning right now, and we're not far off. Today, we're beginning to see and realize telepresence in a lot of the things we do is not complete. And COVID did speed that process quite up, where we have people working remotely in different places. One of the things that I like about telepresence is the unlimited workspace. If you work with spacecraft or you work with planetary rovers, to operate them, you need multiple screens just to be able to see your images, be able to analyze data. But with a telepresence goggle or anything, you have infinite space. So it does open space, and it creates a huge workspace for you to be able to operate in. And that's one thing I like about it today, because it's very practical. I don't need a single screen to look at my data. I can wear my goggles, and the whole room is my screen. So one of the things we'll talk about is what is telepresence, the perception and action at a distance, and how it is significantly changing our lives. We'll look at VR, AR, MR, and the techniques for 3D reconstruction, right? As consumers of telepresence technology, we want to make sure we understand the limitations of this technology and the context in which we can use them. And I'll give you examples of how we've been exploring and using these technologies with examples across NASA. And obviously, I'll present some results that we've in real world use of it and how we've also been able to deploy it in education. So telepresence, as I said earlier, is the perception and action at a remote physical location, right? And basically, you want to be able to operate in an environment that is remote. you want to be able to sense that environment, and you want to be able to send actions that the robot or the person can take those actions. And it's also a very collaborative effort, right? It's not like a one-way traffic. You get data back and forth, and you get decision being made between the two agents or multiple agents in some of the cases. So I think I would like to start by defining what it is. It's a set of technologies which allow a person to feel as if they were present, to give the appearance of presence, right? Or to have an effect via telerobotics, in this case, in a place other than their true location. So I want to be here, but I want to have a present probably in Pasadena, several tens of 10,000 miles away, to be able to feel present within an environment that a robot is operating or a human is operating, and I want to be able to interact with them like I'm interacting with somebody in this room. So to be able to do that, we look at an architectural block diagram as to how the framework in which we work in. So here I'm showing you on the left side here, 3 rovers that will be sent into the lunar surface shortly once we get our CLIPS landers to land correctly. This is CADRI mission. And CADRI mission has got 3 mini robots that have got ground penetrating radar and is going to do the first multi-agent science on another planetary body. So you can imagine, and they have cameras, they have other sensing modalities as well. So you can imagine they get their data, and we typically have a low bandwidth data transmission, and we have a high bandwidth data transmission. There are delays, this information come in, and then you have humans either on Earth or on the moon, right? And then they have this multimodal interface as well. They're getting this data, and then they're trying to interact with an autonomous set of robots to do exploration. To do that, you need to have a distributed decision manager. And this is where we spend most of our time. Where do you put this manager, right? Do you put it with the robots or do you put it with the humans? All this is all dependent on what you're trying to do. So we've done a lot of collaborative decision making between the remote human agents and autonomous robots, or even multiple autonomous robots on different planetary bodies or different locations. How do you share information? How do you make decisions in a seamless way that we do as humans when we're working together? And the information that you have for the humans is typically time delayed because you can't get instantaneous. So you're looking at audio, some artificial intelligent environment, a virtual environment, maybe a twin environment, avatar, 3D construction of where the robotic agent is operating, so you can be able to visualize this and have a presence in that. So we look at VR, AR, and MR, and one of the most challenging part is tactile, right? So humans just don't communicate with just audio and visual. We like to get this tactile feel, and it's been a challenge in this type of telepresence. So this is an architecture we're looking at, and we've looked at distributed decision-making architectures. We've done a lot of trade that the decision manager be on the robots, or should it be on the ground? And this kind of goes back and forth depending on the type of implementations that you want to instantiate. So one of the most important things is the continuum of immersion. Do you want to be fully immersed in the agent's environment? Do you want to be partially immersed? So this is also a continuum that you have to explore depending on the application. I'll show you several applications where we're looking at these technologies. So there are 3 main technologies today that will allow you to have this immersion. The obvious one is virtual reality, right? And it creates a completely simulated environment that a user can interact with, right? Typically using headset, motion controllers. And this fully immerses you in the digital world, right? So you're not being able to see the actual world. Everything you see is reconstructed. The other form is augmented reality, where you can see with your eyes the real world, at the same time you can see the virtual world. So this, you can blend the two together, and this is also very useful for different applications. And then you have the mixed reality world, where you combine both the virtual reality and the augmented reality to be able to interact with this agent. So as we can see, the boundaries between virtual reality, augmented reality, and mixed reality is kind of a blending, and it's kind of blurring. And this will lead to very interesting application fields as we move along in terms of telepresence. But as consumers, we want to make sure that we understand the limitations of these gadgets and in what context that we can use them. And I'll show you several examples which we have done that. And the other aspect of this is also the different ways of how these things operate. For an AR system, we have what we call optical see-through, right? That's the HoloLens. It means you can see things virtually at the same time you can see things with your eyes, right? So it makes a very, it's very important in cases where the human is assembling something with a robot, right? If you're seeing everything through a video link, which I'll talk about shortly, and you drop something, there's a delay before you can catch it. But if you have your eyes and the camera at the same time, combining that can be very useful in places where you're doing construction, assembling things, and it helps make sure that you can see both the virtual world and the real world as well. The other one that is very popular, this is what we call video pass-through. So if you look at the Vision Pro from Apple, for example, it's got 14 cameras, about 6 of them are aimed at your eye, and basically it's all video. You actually don't see the real world. It reconstructs your real world through the video. These are certain advantages, but one of the strong disadvantages for this is when you are interacting with a robot, things can drop or you can miss things. It's very important as a human to be able to see the physical things dropping, but it does give you a much better field of view, just not with your eyes, right? So immersive pass-through allows us to have higher quality visual and precise blending of digital content with the real world. The virtual elements can appear more realistic compared to a transparent AR display. And since the real world feed is captured by the cameras, developers can manipulate the scene by adjusting the lighting, the colors, and adding special effects. And it's good for where you have very complex interaction, like I said earlier, in construction and moving boulders and other things that. And with that as well, it also offers you a little bit of privacy as well. So that's one of the advantages of that. The cons of a video pass-through is that even with high-resolution cameras, the real world is seen through a camera. So it's not sharp, sometimes it's not very clear, and often there's a loss in data transmission. So that can lead to some really interesting problems when you're working with a robot in a critical assembly work. And then you have latencies as well. And then in addition, the field of view can be very limiting, depending on how the goggle is constructed. And one of the biggest weaknesses for us is that it's very bulky, right? So you can imagine an astronaut, somebody trying to operate, and they have this bulky thing on their head. It can be very disorienting sometimes as well. The other aspect of telepresence that we want to look at, and we've been looking at, is what the 3D reconstruction technologies, right? When you put on these goggles and then you take these images, you want to feed it, you want to recreate the environment, how you reconstruct the environment. There are basically 3 typical techniques that are used. We use photogrammetry quite a bit because it allows us to take pictures from multiple points, build our 3D clouds, be able to put polygons to it and create a very high resolution, very accurate model, right? So this is very good for man-made structures. For example, if I look at a space station, we build a space station, we know where everything is, right? We can create a very accurate model of it, but it's data intensive. The next technique is what they call the NERFs, or the neural radiance field. Basically, instead of taking the points, we're using a volumetric assembly, right? So 3D volume to actually model the scenes. This is very fast. It allows for very good control of lighting, and it's also very efficient in terms of processing, because you can use very sparse data, and you'll be able to get something that is fairly realistic, but actually not very accurate. So if you're looking for speed, for example, if you're exploring an environment, what you can do is, like humans usually go to a place and they do a quick look around. It's very good to reconstruct that quickly using nerves. Then if you want a detailed model, you move on to the photogrammetry. But you cannot use the nerves to be able to do very accurate, precision robotics assembly work. And then the very latest one is what they call Gaussian splatting, right? So Gaussian splatting also using radiant fields, but it actually takes every point in the point cloud and then models it using ellipse, or in the 3D form, ellipsoidal. So what it can do is that the more details it needs in a particular area is going to fill it up. And the places where detail is not important, it's loosely done. And this allows you to do 3D editing actually on the fly. And it's much faster than nerves. And it uses basic linear regression methods to do the curve fit, right? Instead of using deep learning to learn the data, this can do it on the fly using linear regression methods. And the splatting renders very quickly, and it allows you to have very detailed, in real time, be able to model very complex structures and in much better details. So in the case of exploring something like the lunar surface, looking at caves, we believe Gaussian splatting offers us a much faster way of doing it in real time to be able to make decisions and look at very complex structures, right? If we're not interested in the accuracies of photogrammetry. So, as I said earlier, we want to be very good consumers. So we look at what is on the market, what the technologies are. We analyze the technologies. We look at their pros and cons, and then we try to use them in different application areas. One of the areas that we look at is scientific exploration and research. We look at satellite maintenance and repair. We look at space mining. We look at space tourism and space construction, and education and public engagement. I have to be honest, we've put in a lot into education and public engagement because we realize that using this thing is able to engage more kids into the STEM field. They don't see things as remote. They can interact with this environment. They can look at our robots and our rovers in different ways, and we can be able to engage a lot of young kids. So what I'm going to talk about is things that we've done in the past decade and things that we're doing today. We're trying to use telepresence in public outreach. We're also trying to use telepresence in how we build our robots. And I'll show you a way that Clipper that was supposed to launch sometime this week, but I think the hurricane is going to delay it, is how we're able to work with the Applied Physics Lab on the East Coast to be able to virtually look at a spacecraft and be able to build it virtually from using telepresence from the East Coast and the West Coast, engineers looking at things, moving things around is very exciting. So this is something we did a few years ago. Let me see if I can mute. Is your audio working?
Also the automated data processing pipeline that produces that terrain product.
You know, with the 2D images, you didn't really have a depth scale, so you didn't really know how far things were, and on-site just completely has changed that now.
So
and then
here
just being
we're
able to
using
look
the
around and see it,
HoloLens.
and very quickly as a geologist gives me a sense of the place.
Nothing replaces standing up with this on your head, this HoloLens system on your head, and seeing it real scale. And you see things that you just can't see at this scale. That's really powerful.
And here what I mentioned is
OnSite
also the
supports a
workspace.
multi-user capability
Instead of using the screen,
that allows
your
scientists
whole
in
room is
different
your
parts of the
workspace.
world to meet together on Mars and have a conversation about the geology of Mars in a shared spatial context. To make this experience
So this we did about a decade ago, and the scientists were really excited. These are images that I remember acquired on Mars with Opportunity rover, and we're able to play back with the scientists to put themselves on Mars as a telepresence. We have people in Europe and people in the States able to collaborate to be able to select rocks that they want to go to. It gave them a very unique perspective of exploration. And as I said earlier, we've done a lot with Buzz Aldrin on public outreach. So here, we set up a room where we were able to educate people to be able to feel present on Mars, what it feels like to work on Mars, to walk, to explore, and to grab the attention of the young kids to get involved in STEM. It was very, very successful. There were always long queues, longer than Disneyland, which is always a good measure. So here I'm going to show you typically how we operate a rover on Mars, right? We need a lot of screens. And we want to take this process and turn it into a telepresence operation where we can be able to get the scientists and engineers to walk on Mars, interact, and be able to plan a daily activity. So a daily activity on Mars, you have a screen, you have multiple screens trying to plan a drive using what we call mobility sketch, which is just like you're playing a video game, look at the map, be able to do all the obstacle avoidance maneuvers, and draw exactly what you want the robot to do. And you do all this by looking at multiple screens using DEM, and then you can use some of the goggles to do it. Our goal is to take this process and make it actually a telepresence approach, where you can all sit in the room like this. The whole room is your screen, and be able to pick points, drive along with the rover as it's driving, as it's using the robotic arm, walk around the rocks as the robotic arm places the instrument on the rocks, and be able to discuss it with the scientists as to what can happen, what can go wrong, and make decisions that way, instead of looking at a flat screen and having that discussion. So we made this video just to illustrate how tedious it is to do it today, and what we need to do to make it in a telepresence approach. In addition, we believe that in the future, all robots or anything that moves has to be telepresence qualified, right? So if you have a car, can you drive your car using telepresence? So you have to think about what type of sensors you need to put in your car or your robot so that you can operate it in the telepresence way. So we think there are going to be standards coming up about telepresence instrumentation of homes, of cars, of anything that you use that you can operate it in a telepresence sense. So here you can see there's a lot of complicated sequences that have to be built and visualization that have to be built to do this. But if we can put in the telepresence kind of framework, we'll be able to do a much better job. And this is Protospace. It's something we've been working on for years, how we can get engineers to collaborate to build a robot, right? So here, I'm showing you building the rover, getting things from CAD, multiple engineers, using VR and AR to actually assemble the robot from different locations. Sometimes they sit in the same room, they're able to move things around, they're able to check how things fit, and we've used this, we use it on Clipper that is going to be launched hopefully this week or next week, to build the whole spacecraft, to be able to do assembly, to make sure things can fit. Engineers on the East Coast and APL, engineers at JPL, can have a meeting where they are actually using their CAD models to fit things together, to operate, to do a design. And this has been very, very successful. We have a few papers on this. And we think this is going to be the future. As we're working with JAXA on the pressurized rover for the moon, we believe we're going to use the same techniques. We don't have to be in the same room. We can take our CAD models, we can assemble things, we can look at how things fit, we can look at volumes, we can look at other constraints as well.
Create an immersive and collaborative workspace.
Then the area that I said we've been very successful with Mix is public engagement. Being able to take our existing spacecraft and getting kids and other people to interact, even engineers. When we do orientation these days, we have new engineers. They're able to take they're able to take a rover, they're able to wear their goggles, they're able to experience and be able to examine how the rovers are built, how they work, and they're able to ask more detailed questions about the operations of the rover. So this is something that is online. Actually, it's in the App Store that you can get. And you can pick up the rover, you can go to any location on the rover, it will explain to you exactly how it works, how it was built, the details of it. So we in public outreach, the VR and AR has been very, very successful in engaging schools and students. Another area that we've investigated using AR is in anomaly resolution. So as you can imagine, you're operating a rover on Mars, you have an anomaly, you want to be able to figure out what happened. You typically will look at a flat screen, we have all the telemetry coming down, you're looking at the current, you're looking at the torque, and you're able to tell this is what happened. But what I'm showing you is that the data that came from the spacecraft, this is a true anomaly on MSL. You're plotting the current in real time on all the wheels. You're looking at it in the context of the terrain. The terrain will show up very slow, shortly. And then you as an engineer, you can walk around the rover, you can look at the configuration of the rover. Here, it actually had a problem with the left front wheel. So you had to go check why did it have so much high current. You can see its interaction with the terrain by walking around it and being able to identify exactly what happened. So we're also using that in anomaly resolution, especially if you have a spacecraft with very large solar arrays that you're deploying in deep space, and then things get stuck. You can walk around it, you can look at all those configurations rather than just looking at 2D angles. And then this is one of the most exciting one. So typically when we build our systems, we don't build them in a modular fashion so that they are repairable. So this is this is the Cold Atom Lab instrument on the ISS, and we wanted to upgrade it. And to do the upgrade, you need the astronauts to upgrade this, but this is built and is buried right into the module. To be able to remove it, engineers have to give incredible detailed instructions for the astronaut to do it. So JPL and Johnson Space Center and a few came up with the idea to use the HoloLens to do it. So there's an astronaut on the space station. We put markers in different locations. And on the ground, we're visually seeing exactly what is coming from the HoloLens. And they're able to direct the astronaut step by step to remove over 100 fasteners, to remove several cables. And all this is done from the ground, from the astronaut. So you can imagine the astronaut is one agent remotely, the people are on the ground, and you have this decision space that you have to make a decision. Depending on what the astronaut is saying, you have to give them a different direction. And it was very successful that the astronaut was able to actually, something that even our technicians on the ground take several hours to do, was able to disassemble the whole package, repair it, put in the new board, and be able to assemble it, and it's still working up to today. So this is one of the most successful use of telepresence between one human to the other human, several thousands of miles away, and it was really a very complicated. I can't emphasize how complicated it was, very complicated, because you can see these wires are not meant to be disassembled, right? You put this thing together, you think it's going to work forever. If you don't need it, you put it back on the space shuttle or Dragon and then bring it down to Earth to be repaired. But here, we were able to take advantage of the technology to be able to do this kind of repairs. So this gives us a lot of confidence moving forward that telepresence can be used across what we call the life cycle of the project. When we start a project by even coming up with concepts about how to build a spacecraft, we can get our engineers to use the telepresence approach from all over, from any remote location, and be able to build a spacecraft, come up with the concept. Once we start doing the CAD models, we can get our engineers to use telepresence to actually take their models, fit them together, do fit checks, do volume checks, and be able to actually look at very complicated cabling. Cabling is one of the most challenging part of building a spacecraft, right? Because these are soft goods. You want to make sure that we usually spend tens, or if not millions of dollars, building mock-up of the spacecraft to run the cables, right? Because you just want to get it right. If we can use telepresence to do that and be able to do it virtually, be able to run these cables, see what it looks like, it's going to save a lot of cost, and it's going to speed up the process. So telepresence is not only meant for the operations of the spacecraft, it's meant for the whole life cycle development of the spacecraft, and in addition to operations and science exploration. And then this is another area that we've used telepresence. We worked for DARPA 2 years ago on what is called the Subterranean Challenge, where DARPA wanted robots to go into caves, map the caves, and do exploration. JPL was very successful in the first part of this operation. We're able to use Spot, the dog, the robotic dog from Boston Dynamics. We're able to put a light on it, we're able to put it in the cave, and we're able to do real-time mapping of the cave and be able to navigate the cave using our VR back and forth, and we're very successful in most of the navigation within the cave between the human and the robot. And once again, it's the challenge is where the decision is made. Is the final decision module on the robot, or is it with the human? And this is the trade that is something we've been doing for a while, which I think most people call sliding autonomy, right? Where do you put the autonomy? Because this autonomy is sliding from the remote human to the robot, and it comes back and forth. Where's the most efficient way to put this? So this is a kind of things that we've explored in the space arena for telepresence. And hopefully this talk, we want to have more discussion about that. I know that there's a big area in medicine that we're looking at as part of the IEEE telepresence group. We're looking at it in medicine, we're looking at it in other construction. My emphasis here is on space, how you can use telepresence to advance our space exploration, to make it more efficient, to make it more cost effective, in addition to able to draw more youth into science and engineering, show them how exciting it is, rather than just seeing things in 2D space, for them to know that you can interact with this agent and can make significant progress. I don't think my timer here is working, but I think I'm doing good on time. It still says 45 minutes. Okay, so with telepresence, we want you to imagine, the possibilities for science and exploration that can be achieved together in our solar system with telepresence, right? You can imagine walking on Europa. You can imagine digging on Europa, digging through the 1 kilometer ice to get to that ocean that we believe has life. I think it's just limitless, right? And it can facilitate the transfer of human intelligence to machine intelligence. One of the challenges that once you build something and you just fly it, you have to update the software. But here, if you build the right framework, the human intelligence, the robotic intelligence is going to be a dynamic thing that is going to shift back and forth in a continuous realm. And it's going to also revolutionize the way we do work in terms of workforce. We don't all have to be co-located. We don't need rooms full of multiple screens, right? We can use the space as our screen. And that to me is very, very exciting. And as I said earlier, the economic impact, impact on engaging the workforce. And this is beyond outsourcing. You're not outsourcing to someone, you actually have people distributed remotely, and they can get the work done. And it brings great opportunities for distance operation. And I think we're very excited about this technology. I can tell you how excited I am, and the potential impact of telepresence on space exploration and making space exploration accessible to a lot of people. Because a lot of people are not able to look at just telemetry. They want to feel exploration. They want to be able to walk on the moon. They want to be able to see things with scale, like one of the scientists was saying in the movie. So here I'm going to stop and then see if anybody have any questions. I enjoy more interactive talks.
Okay, now I open the question to the audience, so you may ask question. Yes.
Hello, I'm Frank Flemish, former NASA Langley, now Aachen University, and Fraunhofer. We are also supporting the European Astronaut Center also on this question of telepresence. And I have about 100 questions, so we don't have time for that.
We have time for 200, but that's okay.
200. But one question that we are really struggling with, and I'm really curious on your take on that. We have this time delay, and you mentioned mission to Moon, Mars, and beyond. On Moon, it might still be solvable. On Mars, it's really substantial. So we can do telepresence somehow with this time delay in a model-based world in order to experience this and then send all the data to Mars and then interact with it. And the question is now, what happens on very fast-paced events that happen then on Mars? Because then we are behind the time curve somehow, and we can't react in telepresence. What we are discussing in the moment is then interacting also with autonomous functions and enabling them then to react on behalf of the human fast enough, and then to get into telepresence once again with the time delay a little bit later. But that's a quite tedious process. How do you authorize then these robots? What do you do if you have humans already on the ground? And I'm wondering how you handle this tension field between telepresence and autonomy.
Yeah, so most of the robots that we intend to work with telepresence, we want them to be autonomous, more autonomous than the Mars rovers that we have today. So we do expect them to have a very high level of autonomy, but we know that we cannot put every bit of autonomy into it because they are corner cases. So when they get into trouble, we want them to call home.
Right.
But we can use telepresence to give us a better understanding of the situation, right? So for example, I can give you an example where I was driving Spirit and we got a rock caught inside the wheel of Spirit. So the wheel is locked, okay? It took us several sols, which is several days, to figure where the rock was because you cannot see it. But if we had a telepresence, which we've done, we play back and we're looking at it, we can see exactly when the rock was picked by the wheel. Right? And then we can be able to help the rover recover from that.
Yeah.
So I don't think it's every time that you want to do things in real time. The sensing is very important for telepresence.
Yeah.
What sensor suite do you put on an agent so you can get the right information, so you can get the human to be able to comprehend and then solve the problem?
Right.
So not everything is going to be real-time telepresence. We expect there to be significant delays, but we want the decision-making to be very dynamic.
Right.
Yeah.
So we call this virtual telepresence, and we are then working with a digital shadow.
Yeah.
We always try to keep a digital shadow of the spacecraft, for example, of the astronauts. So in case we get a time delay or maybe even an interrupt of the telecommunication, that we can work in presence with the digital shadow. And this is what you call also telepresence. That's,
So the digital shadow, it's a digital shadow, but it's not the whole spacecraft is not updated at the same time. We only update the part of the spacecraft that has changed.
Yeah, that's right.
Is that what you're talking about?
Yeah.
So the update is very fast.
Yeah. Okay. Thank you for clarifying this.
Okay, thank you.
Any more questions? Yeah, any more questions? We have plenty of time. We've got another 20 minutes.
Right.
Yeah. Any more? Okay. I have one question.
Okay.
So normally I don't know much about this outer space kind of application, especially Mars. When you talk about the delay, how big is the delay in terms of time frame? Maybe 1 day, 2 days, or?
So in terms of Mars, when Mars is closest to Earth, our delay can be up to 5 minutes.
5 minutes.
Yes.
Not that.
But when Mars is very far from Earth, it can be several, tens of minutes.
Okay.
Yeah.
Right. Okay.
But when we go to Europe or the outer planets, we expect probably an hour delay, and on top of that, we don't have a lot of bandwidth. So we have very low bandwidth data. So you have to wait a long time to be able to assemble. That's why we're talking about the shadow. So here we only want data to update what has changed with the spacecraft, not the whole spacecraft. Yeah.
What is the carrier frequency of the transmission?
That's X-band. So we use UHF and X-band. Yeah.
Okay.
So X-band is for direct to earth and then UHF. Yeah.
All right. Any more, guys? Yeah, we have one at the back.
First of all, thank you for your presentation. And I have a little question. Do you think that in the future satellites will be positioned closer to Mars in order to carry servers to offload the processing, image processing from Mars and make local decisions faster?
So there are architectures that have looked at shared functions, right? So for example, when you look at these robots that I'm showing you here, that cadre, what they do is that they distribute the workload amongst themselves. So they're not all doing the same thing. So we believe that when humans, for example, if you look at Artemis, there will be humans around the orbit of the moon and the spacecraft, right? Working with robots on the surface. The data, the functions will be shared between the spacecraft in orbit and the robot on the ground. So we've been thinking about that type of architecture where we share the workload functions depending on processes. But you also have to say that it's a trade because you have a communication issue. So the more, and then you have a power limitation, the more data you transmit back and forth. So most of the approaches we're looking at today is transferring knowledge. We don't want to transfer raw data anymore. When we do science, we want to be able to do the science, actually get the robot to use artificial intelligence to actually do the science and send the science data results back. If the scientists on the ground want to get the data back, they can actually request the data to collaborate the findings. But we don't want to be transmitting a lot of data back and forth because that takes a lot of energy.
Okay, thank you so much.
Any more? Okay, I got one more question. Okay, so especially on the Mars, do you have like robotic system which collaborative robotic system on Mars? They're like more than one robot cooperate together.
So on Mars, most of the rovers that we've sent on Mars, currently we have 2 rovers running on Mars, right? We have the Mars Science Vehicle, and then we have the M2020 Perseverance. So the only collaboration that our rovers have had on Mars is actually sending image from one rover to the other, and it all is through the orbiter. But we've not had rovers actually talk to each other and do collaboration. The first collaboration that we're going to show with robots on any planetary body is going to be cadre on the moon. Yeah.
All right. Any more, guys? Any more? Do you have constraint like because on Earth it's different environment?
Yes.
Maybe on Mars different environment in terms of temperature, pressure, kind of things. And so how does this instrumentation on board of the robot react to this? Do you have any
so you're talking about the environment conditions on Mars are very extreme. We go from very cold to very hot. We're talking about up to -103 to +20 degrees Celsius. So they're extreme. So when we build these robots, we do go through what we call an environmental qualification. So we have chambers that we can simulate. We can actually put the spacecraft in the chamber and run all this, do all these things 3x time that the robot is going to see. So that's what we call environmental qualification. And then we do have better models on Mars, because on Mars, if you're on Mars, it's like you're flying, you know. As the sun rises, your ear is going to pop because the pressure is changing, right? So we have a better understanding of that. We have very good weather models on Mars. You know, I can go in and tell you today, this part of Mars, what the wind speed is going to be and what direction it's going to be going in.
Okay.
So we have very good understanding. And then we can, in orbit, because we have a lot of assets in orbit, we're able to predict dust storms. So we can predict a dust storm season. We know the dust storm is coming. We know a big dust storm is coming in 2028. So what we can do is we can put our rovers in the safe mode to be able to survive those. Okay. But now most of our rovers are not using solar arrays. They're using RTG, radioisotope thermal generators. So we don't have that issue that we had previously of dust accumulation.
Okay, one more. Because since they don't ask questions, so I can ask you a question. What's the toughest problem that we are facing in controlling the robotic system there?
What is the toughest? Okay, so I've been fortunate enough to work 4 rovers on Mars and 2 landers. I would say the last lander one that we did was the InSight lander that we work with the Europeans, or we work with Canes and DLR, which is the German Space Agency, and the French. And we put a seismometer on Mars, So that was the first seismometer that has been put on Mars to see whether there were Mars quakes. And we made a very important discovery that there were Mars quakes. We were able to tell the core of the core of Mars is molten. So that changed the test box. And we're able to tell about the crust, the thickness of the crust. And we were able to kind of basically tell you everything about Mars, the interior of Mars that we didn't know. One of the challenges with landers is that we use solar arrays. And then with time, dust built on the solar arrays. But typically, we design these missions for 90 days. We look at the accumulation of dust. We have models of how fast dust is falling from the atmosphere of Mars. And the model was very accurate. So we're getting so good data. We were there for over 2 years, but we wanted to extend it and wanted to figure out how to clean the dust of the solar array. So we came after technique, my colleagues and I, and we realized that there's a scientific process called saltation, right? So for dust to be cleaned, you actually, when the wind blows, the wind doesn't just blow the dust because the forces that hold the dust to the surface is very different. It's actually the particles that the wind is carrying that hits the surface, that cleans the surface. So we thought we're clever, so we use our scoop to scoop dust and then wait for high winds and then start dropping it so that the particles from the drop will clean it. It did it for a while, but it didn't clean fast enough for us to recover. So that was challenging and fun.
All right.
Good engineering challenge.
Yeah, one more.
Okay.
Okay, I'm digging now. Okay, so in terms of, I'm pretty sure you also use battery, right? To power up the robot? Yeah, or you just use solar panel to power up the...
What power do we use to? So the rovers, the current rovers on Mars, so in 2004, the rovers that we sent, Spirit Opportunity, had solar arrays. And we're fortunate enough that they last over a decade. The reason for that is, on Mars, they are what we call dust devils. And these dust devils, we didn't predict that. The dust devils come in on a fairly regular cadence to clean the solar arrays, so they lasted. The next 2 rovers we sent, we used radioisotope thermal generators. And they're not nuclear plants. They're very different. So what happens with a radioisotope thermal generator is that when it's decaying, there's heat generated. That heat is captured and converted into electricity. Okay. And that electricity is put in our batteries. So we've been using RTGs for a while, and we're using plutonium-128, and it's got a half-life of several tens of years.
All right, any more questions from the audience? Because I already asked many questions. Any more? All right. Okay, if no more questions, we'd like to say thank you very much to Dr. Ashitey. Round of applause for him.
Thank you.
Thank you very much.
Okay, thank you.
So with that, we'd like to conclude this session. Thank you very much for attending this session. Thank you again.